In a series of related video modules, we have talked about the basics of queuing systems and how they work. We also introduced the queuing formula for MMC systems, and we talked about the assumptions and analysis of Jackson networks. And also we showed how to solve a queuing network problem by hand. In this video, we're going to perform what-if analysis using Excel. In other words, we're going to evaluate the performance of the system under different arrival rates into the queuing network. And also, we will learn how we can use simulation to verify our queuing results. So in this video, I'm assuming that the viewer has a basic knowledge of queuing networks and queuing systems. So the first three items that I have listed here are necessary for the viewer to know in order to be able to fully understand what we do in this video. So if you are already familiar with queuing theory, or you have watched the modules that cover the first three items, you're good. Otherwise, I would suggest that you stop this video and watch the related videos and learn about the basics of queuing systems, and then come back and continue the current video. But the fourth item is not necessarily a requirement, but it would be really helpful to understand the queuing formula that we use in our Excel model. So let's have a look at the queuing network that we're going to solve in this video. As you can see, we have 5 servers in this queuing network, servers A through E, and we have 2 sources of external arrivals into this network. So we have lambda 1 and lambda 2 as the 2 arrival rates that correspond to the 2 arrival processes that we have here. And we have probabilistic routings. So, for example, 25% of the parts that are processed on A will go to server B, and 75% will go to server C. We have our server information in this table. So we have the capacity of the server and the service rate of each server, denoted by mu, summarized in the table. So for example, for station A, we have a single server, and the server can process 150 parts per hour. And you can see the capacity and the service rate for the other servers on the table. So the arrivals are assumed to be Poisson, and our service times are also exponentially distributed. Both arrival and service rates are represented in the units of entity per hour. As you can see, the assumptions of this queuing network are in line with a Jackson network. So as I mentioned at the beginning of this video, we have solved this queuing network by hand in another related video module, and in this video we're going to perform more analysis using the same queuing network. So here is the queuing model of the same network that I have developed in Excel. So as you can see, I have highlighted the parameters of the model in yellow, and my outputs, or the performance measures that I'm interested in green. So my utilization for each server, number and time at each server, and also number in system and time in system for the whole network. So what I would like to do with this model is to basically see how the performance of the system changes with different combinations of lambda 1 and lambda 2. And I would like to show you guys how you can use Excel's data table to perform such analysis. So what I'm going to do first, I'm going to choose one of my performance metrics to do this what-if analysis, and I'm going to choose time in system. So I want to see how time in system changes based on different arrival rates, but I would like to see my time in system in minutes, so I'm just going to multiply it by 60. So 8.43 minutes is the time in system with the current parameters, and I'm going to change my to arrival rate, so basically lambda 1. I'm going to change it from its current value, 115 per hour, to 134 per hour. And I'm going to change or vary my lambda 2 from 135 per hour to 145. So this is going to be my lambda 2. So let me make these bold here. So in order to complete my data table, I just need to select all my cells here, go to the data ribbon, what if analysis tab, and data table. And I will need to tell Excel where these parameters are located in my Excel sheet. So in the rows, I'm going to have lambda 2, and in the column I have input lambda 1. So I'm just going to select the associated cells for these two parameters. And when you say OK, you will see that Excel automatically calculates the time in system for different combinations of these two parameters. Now, what I would really like to see here is the scenarios where my system becomes unstable. For example, if I see a negative value, or if I see a value that Excel couldn't calculate because I have a 0 in one of the denominators. So in order to identify these scenarios, I can go to my Home ribbon after I have selected my cells, and then go to the Conditional Formatting tab. And then I would like to define a new rule by defining a formula to change the format of these cells. So I'm just going to use a formula to determine which cells to format. And the formula that I would like to use is equal sign R9, which is the first cell in my matrix, greater than 0. And I would specifically want to change the color of the cells where I have a stable system. So I'm going to select the color that I want, and then OK, and now Excel highlights the scenarios where my system is stable, and I can identify the scenarios that result in an unstable system. The last thing that we're going to do is verify our queuing solution using a simulation model of this queuing system. So we're going to start by building the initial simulation model. So I have my source 1 and source 2. I have 5 server objects. Let me zoom out here a little bit. So I have server 1, I have server 2, server 3, server 4, server 5, and I need a sync object, so sync. Then I'm going to connect these up. Let me just move my second source here. So I'm going to double click on the connector. I have a connection that goes here. Server 1 to server 2, server 2 to server 4, server 4 to the sync, and then from server 4 back to server 2. Then I also have a connector from 1 to 3, 3 to input of just, this can be confusing sometimes. Just make sure you go from the output node of the server 3 to input node of server 2. And then server 3 to 5, 5 to the sync. And I also go from the second source to the input node of server 3. And it seems that I have all the initial routings in place. So let me just go ahead and run the model just to make sure that I'm not missing a connector. So I'm just going to run in a faster speed. So it looks like everything is connected. The next thing I'm going to do is input the parameters for my objects. So I'm going to start with my two sources. So I have calculated in this Excel sheet the inter-arrival times in minutes, and we know everything is exponentially distributed. So we can either use these values, or we can simply use 1 over the rate in our expression. So I'm just going to, for the sake of simplicity, for my first source, use 1 over my arrival rate in hours, and this will give me inter-arrival times in the units of hours. For the second source, I'm going to have a random exponential with mean 1 over 140, and I just need to make sure that I change the units to hours. So I have my arrival processes set up. Now I'm going to go ahead and input the parameters for my server objects. So again, everything is exponentially distributed. So for the first server, I have random dot exponential, and I need to input the mean, which I have calculated here. So for the first server, it's 0.4 minutes. And I'm just going to copy this expression because I know all my other servers also have an exponential distribution, but just with a different mean value. So for my second server, I have 0.5. For my fourth server, I'm going to have exponential with mean 7.5. That's server D. For the third server, I have exponential with mean 0.25. And for the last server, I have exponential with mean 0.75. And before I forget, I need to change the capacity of the servers that have more than one server. So I know server, let me go back to my table here. So server 1 has 1 unit of capacity, server B has 3. So I just need to change my initial capacity to 3 for server 2. C is 1, D is 4, so server 4 will be 4. And I have 1 unit of capacity for server 5 and server C and server A. The last thing I need to do to complete my initial model is to modify the selection weights for my connectors. So I know 25% of the parts go from 1 to 2, and so I can either put 25 for the first connector and then 75 for the second one, or alternatively I could have just used 0.25 and 0.75. As long as the proportions are right, the routing will work correctly. So the next thing is from C to B, I have 0.7 and 0.3. So this time, instead of 70 and 30, I just used 0.7 and 0.3. And the last thing is this feedback loop. So 0.3 and 70% or 0.7 go to the sink. So here I have run an experiment with 30 replications, each of length 300 hours, and 100 hours of warm-up period. And I have filtered out the values in my pivot grid that I don't care about at this time, so that I can compare my simulation results with my queuing results easily. So for example, for number and system from simulation, I'm getting 35.16 with a half width of 0.99, while from the queuing solution, I'm getting 35.87. And you can go ahead and compare the other values, like the utilizations and time and system. And in fact, when you do that, you will see that our simulation results are pretty close to our queuing results. So we are now confident that our queuing calculations are correct.